So in this question, we have a graph. So right off the bat, we'll do an Oizerga on this. O-Y-X-I-R-G-A. So the origin, yes, we are at 0, 0. That's good. Y-axis is force. X-axis is x, or the distance or displacement. The intercept, yes, there's a y-intercept that at x0, f is large and positive. And the x-intercept is that at some value x, f equals 0. So we have f decreasing. What we can read from the graph are the axes, f and x. The gradient is delta x, f over delta x. So that is newtons per meter. The area is f times x, which is Newton meters. So force times distance we recognize as the work. It says that the thing is initially at rest, so V0 equals 0. All right, so which of the following describes how the kinetic energy and the acceleration of the body change with distance? So we could start with either of them. I would just recommend we start with acceleration. So we know Newton's second law tells us that the net force equals ma. And so what we see then is that the force is decreased. The object itself has a mass, and that is going to remain the same. That will be equal. But the force decreases as x increases, so that means the acceleration decreases. If the force is decreasing as the distance increases, well, then the acceleration is decreasing. So that means we're at 50-50 right away with those two. So the question then is, what happens to the kinetic energy? So for the kinetic energy to increase, the kinetic energy, let me write it down here, is 1/2 mv squared. Our choices are decrease and increase. Now we know this 1/2 isn't going to affect whether it increases or decreases. The mass itself stays equal. So the question is, what's happening to the speed or the velocity of this thing as time goes by? Well, there is a force at every moment in time until we get to a distance x. So if we were to look at the velocity distance graph, well, in the beginning, we have a velocity, it says we're told is 0. When the distance is 0, the velocity is 0, and the velocity increases. But eventually, we get to a point at distance x where the acceleration is 0. Well, let's do an RGA on this quickly. We can read velocity and distance, and the slope is delta v over delta x. And so that means is the velocity changing as it's moving, changing its position. And so it is like acceleration. It's not acceleration, but it's like acceleration. In the area, v times delta x is going to be meters per second times meters, so meters squared per second, nothing useful. So we see that the slope in this case is a proxy for, is very similar to the acceleration. And we know when we reach a distance x, the force is 0, so the acceleration should be 0 at that point in time, so the slope should be 0. So we could either have a situation like this, or but in any case, we are showing that this shows that the acceleration would be approximately constant, the slope in this case. So we need to show something where the slope goes to 0. And in this case, we're looking at the slope going to 0 when it's curved like that. But in any case, we can see that the entire time the velocity is increasing. And if the velocity is increasing, the kinetic energy is increasing. Now this question, it's easy to be confused because what is decreasing is the rate of increase. The rate of increase is decreasing. But the value itself is still increasing all the time. And after that force is no longer applied at a distance x, we still have this velocity, and it would keep going at that velocity, a non-zero velocity. So it never decreased to getting closer to 0, it just decreased the rate that it increased. And that's why we are looking at choice C for this question.